Okay, last video. We want to close by reflecting on the question of P versus NP. So we've talked about what the class P means and what the class NP means. We've talked about how P is a subset of NP, but the other direction isn't known. So every deterministic Turing machine is obviously a non-deterministic Turing machine that just sort of never uses the non-determinism, and so P is a subset of NP. The question is, what about in the other direction? When you move to NP and you get, for example, the unbounded parallelism or the demon whispering in your ear, however you like to think about it, can you bring problems from sort of apparently super polynomial down to polynomial, down to the range where Cobham's thesis tells us they're at least conceivably solvable? And the short answer is, nobody knows. Of these two pictures, one of them's correct, either the left or the right. The left has P a subset of NP, and the right has the two of them as the same set. One of the two pictures is correct, but at this point, we do not know which of the two pictures is correct. Okay, so first I want to reflect about, again, NP complete problems, since there's sometimes confusion in a person's mind about the difference between NP and NP complete. So the bean here holds all the language decision problems. Every single language decision problem is somewhere in here, and the problems that are fast, that are quickly solved, are down near the bottom. The problems for which there is an algorithm that is, say, runs in time big O of natural log, or big O of n log n, or some pretty fast algorithms are down the bottom. Algorithms that are problems for which the algorithm are very slow are up at the top. For example, you might imagine a problem for which the best algorithm is exponential or super exponential is up here somewhere. In here is NP. Sorry, NP. I wrote with a lowercase n. So NP, and up here, of course, are NP hard. NP hard means that any problem in here would allow you to solve all NP problems. And right in here, these are the NP complete. So the NP complete problems are those problems, NP complete. Sorry about the handwriting. NP complete problems. Those are the problems that are simultaneously NP and NP hard. That means that not only are they themselves NP, but they in fact can you can reduce any NP problem to one of these. So that if you could solve any one of these, then you could solve all NP problems. Okay, so the question is, if there's a gap between the P area and the entire NP space here, if there's a gap in there, then the NP complete ones are on the far side of the gap. Okay. So first, practical importance. A person who's in here because they're interested in computing, what's the reason to think so hard about the question of P versus NP? So many problems that arise in applications, and many problems that have been intransigent for many years, are in fact NP complete. In particular, CARP demonstrated that many of the problems that people have been struggling with in practical applications fall into this category. So researchers who have been trying to find an efficient solution, say, to vertex cover, and those who have been working on clique found that in some way they're working on the same problem. The two reduce to each other. So we're looking at, something like a vertex cover. It reduces to clique, but also vice versa. Clique reduces to vertex cover. So that if you could solve one, then you could solve the other. By now, the list of NP complete problems includes thousands and thousands of problems, determining the best layout of transistors on a chip, or directing accurate financial forecasting models, or analyzing the protein folding behavior in a cell, or finding the most energy efficient airplane wing. So the question of whether P equals NP is extremely practical and extremely important. It would change, if we found a fast way to solve NP complete problems, it would change the world that we live in overnight. Now, the P versus NP question is certainly the sexiest one in theory of computing today. There's no question about it. It's attracted a great deal of speculation and a great deal of gossip, people being people. In 2018, a poll of experts found that 88% thought that P is unequal to NP, while only 12% thought that P is equal to P. And in fact, when you looked a little closer at the data, the people who had worked closely with the P and NP divide almost universally thought that P is unequal to NP. The expert opinion at this point is, no doubt about it, expert opinion is that P is unequal to NP. But of course, that's opinion, that's not proof. So, we have guesses, we don't have proof. Again, the point of this video is to reflect a little bit on why the problem is compelling. So I want to reflect a little bit on what it has to say about, for example, writing mathematical proofs as an example of a hard problem that you'd like to solve. So in high school, you took Euclid. I mean, you might not have called it Euclid, but it was Euclid. This proves that the base angles in an isosceles triangle are equal, and you can see here that Euclid gives a reasonable argument. It's somewhat detailed. But it is step A follows immediately. Step B follows immediately from step A, and step C follows from step B, and all this kind of stuff. And you come down to a final line that says, hence the angles are equal. Those are the angles at the base. So a proof is a sequence of statements. Statement 1, Statement 2, Statement 3, Statement 4, each justified by reference to some prior statement or some law of logic. You're allowed to say Statement 5 holds because it follows from a law of logic by combining Statement 1 and Statement 4. And then when you get down to the end, the final statement here is the thing that you are proving. Okay, and that's just familiar from high school geometry. So in a proof, we require that all the steps be typographically verifiable. We can mechanically check. If somebody says to you, how does line 3109 follow from line 106 and line 2108? You should be able to mechanically check, should be able to check with a computer program that it does indeed follow from those two-sided rules. So this is illustrated by the work of Russell and Whitehead in the Principia Mathematica from the early 1900s, where they tried to derive all of mathematics from first principles in a way that is completely mechanically checkable. So they did this before there were computers in the early 1900s. Each step describes the line from which it is derived. You can see here the different steps and all the notation. We're not going to go into what the notation means. But nonetheless, you can see that it's immensely detailed work. And in principle, you can mechanically check this result from that result, sort of thing. In particular, what's here appears on page 362, and of course a person's attention is drawn to the final line. Never mind what all this has to say, and it certainly looks like, say, assembly language programming, and there are some analogies. But the final line says, from this proposition it will follow, once arithmetical addition has been defined, that 1 plus 1 equals 2. So they are working at such a low level, such a level of tremendous care, that in order to prove 1 plus 1 equals 2 takes hundreds of pages. Okay, so the proofs are immensely detailed. There's no hand waving. There's no sort of we can see or by this diagram. There's none of that. This stuff can be checked with a computer. So recall the Enchanting Problem, that was a motivation behind the definition of the Turing machine from the first page in the book. It looks for an algorithm that inputs a mathematical statement and decides whether the statement is true. Now, maybe it's a character, but imagine that the job of mathematicians is to prove theorems. Then what the Enchanting Problem asks is if we can replace mathematicians with machines. In the intervening century, we've come to understand through the work of Gödel and others that there's a difference between a statement being true and the statement being provable. Church and Turing expanded on this insight to show that the Enchanting Problem is mechanically unsolvable. Consequently, we're going to change the question from asking for an algorithm that inputs statements and decides whether they're provable. That's a different matter. In principle, it's simple. A proof is a sequence of statements, just like about the base angles in an isosceles triangle are equal. The final statement is the conclusion, and each statement is either an axiom or follows from the statements before it by application of a rule of deduction. In principle, a computer could brute force the question by doing a breadth first search of all the possible derivations. So you start with the axioms, you do a one-step combination of all the axioms in all possible ways. Then you do all possible two-step combinations. Then you do all possible three-step combinations, all possible four-step combinations. This process will generate all possible theorems eventually. Basically, you're doing Cantor's process for counting a very large set, and you're generating all possible proofs. So this process generates all possible theorems eventually. The difficulty is that final word, that eventually. This algorithm is very slow. So you ask yourself, is there a tractable way? In the terminology that we now have, the Enchanting Problem is a decision problem. Given a statement sigma and a bound capital B, we ask if there's a sequence of statements omega witnessing a proof. Okay, so that's exactly what we've been thinking about. Witnessing a proof, the proof has to end in sigma, and we're looking for it to be shorter than the bound. That is to say, we're looking for it to be tractable. A computer can quickly check whether a given proof is valid, and that is to say, proving these things is in NP. With the current status of the P versus NP problem, the answer to the question in the prior paragraph is that no one knows of a fast algorithm, but no one can show that there isn't one either. So we have a problem we dearly like to solve, and we've stated it very precisely, understand it perfectly, and we don't know whether it has a solution or not. As far back as 1956, so before I was born even, as far back as 1956, Gödel raised these issues in a letter to von Neumann. The letter didn't become public until after Gödel died and people looked through his papers. And he says, he imagines, is it possible that there is a machine that runs in time big O of n or big O of n squared? He says that would have the consequences of greatest importance. Namely, it would obviously mean that in spite of the unsolvability of the Enchanting Problem, the mental work of a mathematician concerning yes or no questions could be completely replaced by a machine. That if you had a statement that was in any way possibly conceivably of interest, then you could, if the time to prove it is big O of n squared, you can imagine proving it. You just ask the machine, give it a try, run all possible proofs, and tell me if the answer is yes or no. If the input is only reasonably big, then big O of n squared only takes reasonably long. He says, it seems to me to be completely within the realm of possibility that big O of n grows that slowly, that the big O of n is actually the right answer. Now, I don't know that people working in this area today think that's within the realm of possibility, but the point is that what he says here. It would be interesting to know, for instance, the situation concerning the determination of the primality of a number, and how strongly in general the number of steps in a finite combinatorial problems can be reduced with respect to simple exhaustive search. That's asking the question, P versus NP, can you do better than to exhaustively search? Is there sort of a shortcut? So again, in modern terminology, this problem is in NP. If somebody gives you a theorem's derivation, omega, then checking it is fast. But that we know today, it appears that generating all the theorems is slow. Certainly the brute force, breadth first way is slow. Now, Gödel was extremely, sort of legendarily careful about how he said things. We can develop what he said into somewhat less careful, but perhaps more memorable statements. So I'm going to quote three experts on the subject, and I know you can read, but I'm going to read at least parts of the statement here to try to give a person some intuitive sense, some sort of walk-away sense, some sort of, if you don't mind, marquee sense of why we're so interested in P versus NP. So Cook, of course, the person who originally showed the Cook-Levin theorem, a practical algorithm for solving an NP-complete problem would transform mathematics by allowing a computer to find a formal proof of any theorem that has a proof of reasonable length. That's what Gödel was talking about, since formal proofs can easily be recognized in polynomial time. Although formal proofs may not be initially intelligible to humans, the problem of finding intelligible proofs would be reduced to that of finding a recognition algorithm for intelligible proofs. Similar remarks apply to diverse creative human endeavors, such as designing airplane wings, creating physical theories, or even composing music. The question in each case is to what extent an efficient algorithm for recognizing a good result can be found. That is to say, is there a verifier for composing for great music? If so, then you'd be looking at, if P equaled NP, then you'd be looking at the problem of verifying is the same speed in some sense as the problem of solving, and so we could hope to solve. Scott Aronson. If P equals NP, then the world would be a profoundly different place than we usually assume it to be. There'd be no special value in creative leaps, no fundamental gap between solving a problem and recognizing a solution once it's found. Everyone who could appreciate a symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. Everyone who could recognize a good investment strategy would be Warren Buffett. That is to say, a verifier and a creator would be, in some sense, the same. Avi Rigerson, this seemingly abstract philosophical question, can creativity be automated in its concrete mathematical form? Thus, P equals NP emerges as a central challenge of science. And the basic notions of space and time studied as resources of effective computation emerge as the key objects of study to solving this mystery, just like their physical counterparts hold the key to understanding the laws of nature. So why do we think this question is compelling? And the answer is because it is compelling, because it speaks to sort of the fundamental nature of what can be done. I want to talk about the two guesses. I want to close with the two guesses. So does P equals NP or does P equal NP or not? And we're going to start with talking about people who think that P does not equal NP. A problem is in P if finding a solution is fast, while a problem is in NP if verifying the correctness of omega is fast. From this point of view, the result that P is a subset of NP becomes the observation that if a problem is fast to solve, then it must be fast to verify. But most experts perceive that the inclusion in the other direction is extremely unlikely. So restated informally, the P versus NP question asks if finding a solution is as fast as recognizing one. If P equals NP, then the two jobs are in some sense equally difficult to within a polynomial factor. Most researchers just simply do not believe this. Related reasoning is that there are thousands of NP-complete problems spread across disciplines like combinatorics, number theory, geometry, economics and finance, biology, operations research, etc. These problems differ wildly, bearing no obvious relationship to each other, besides the fact that they're all NP-complete. Because they're all NP-complete, they're all mutually irreducible, so a polynomial time solution to one would give a polynomial time solution to them all. No one has been able to find a polynomial time solution for any of them. So many thousands of people have worked very, very hard on all these thousands of problems, and all these thousands of people are extremely smart, and no one has ever found a fast solution. That's strong empirical evidence. Now, not proof, to be sure, not proof, but nonetheless strong evidence that P is unequal to NP. Let's take the contrary view. Many observers have noted that there are cases where everybody knew, everybody was sure that some algorithm was the fastest, but at the end it proved not to be so. The section on Big O begins with the grade school arithmetic for multiplication. People who were worldwide experts knew that this is the fast way to do it, but it proved not to be right. The Gauss's method algorithm from linear algebra, which runs in time Big O of n cubed, is perfectly natural, has been known for centuries without anybody making improvement. But while trying to prove that Gauss's method is optimal, Strassen found a method that's faster. Instead of Big O to the n cubed, Big O to the 2.81, and in fact has been improved a little bit since then. A more dramatic speed up happens with the matching problem. If you're given a graph with vertices representing people, and connect two people if they're compatible, we want to find a set of edges that's maximal, so that no two edges share a vertex. The naive algorithm tries all possible match sets, which takes 2 to the m checks, where m is the number of edges. Even with only 100 people, there are more things to try than atoms in the universe. We'd never be able to solve it from a sort of physical level. But since the 1960s, we have an algorithm that runs in polytime, due to Jack Edmonds. So the sort of obvious natural thing is not always the right answer. Sometimes there's some extremely tricky, very clever way to do the job. Every day, if you read the Theory of Computing blog feed, there's examples of this where researchers produce algorithms faster than the ones that are previously known. I mean, they scroll by. A person can certainly have the sense that we're only just starting to explore what can be done. R.J. Lipton has this from his blog. Since we're continually discovering new ways to program our machines, why not a discovery that shows how to factor or how to solve the satisfiability problem? Why are we all so sure that there are no great new programming methods still to be discovered? I'm puzzled why so many are convinced that these problems could not fall to new programming tricks, that that's what's done each and every day in their own research. Knuth has a related but somewhat similar take. So these are folks, famous experts in the subject, who are open to the possibility that maybe P equals NP. And I'll read Knuth's. Some of my reasoning is admittedly naive. It's hard to believe that P is unequal to NP, and so many brilliant people have failed to discover why. I mean, the problem has been around since 1972, and some of the people who are frighteningly smart have tried it and not had any luck with it. On the other hand, if you imagine a number m that's finite but incredibly large, then there's a humongous number of possible algorithms that do an n to the capital M bitwise addition, shift, bitwise or addition or shift operations on n given bits. It's really hard to believe that all of them fail. My main point, however, is that I don't believe the equality P equals NP will turn out to be helpful even if it is proved, because such a proof will almost surely be non-constructive. Although I think M probably exists, I also think that human beings will never know such a value. I even suspect that nobody will know an upper bound on M. Mathematics is full of examples where something is proved to exist, yet the proof tells us nothing about how to find it. Knowledge of mere existence of an algorithm is completely different from the knowledge of an actual algorithm. So again, most experts think, I mean, if they're going to put money down, they're going to put it on P is unequal to NP. But there are at least some people who are worldwide experts who are open to the possibility that P equals NP, although they're not betting on, most folks are not betting on cracking the problem tomorrow, and it turns out to be like Goethe, or at least seemed willing to entertain, turns out to be big O of n squared. I think there's not much belief that that's right. Okay, so that ends our discussion. So I hope you enjoyed the course.